Hello, everybody, and welcome back to BioSC 140 Human Physiology. This is Laboratory 2526 Respiratory Physiology discussion video. All right, so let's start with the Biopack. So, with the Biopack lesson, we had this strap around our subject's chest, which measures chest expansion and contraction. And we have this thermometer or thermistor underneath the subject's nose, measuring the temperature of the air as it travels in and out of their nose. We're going to have our subject breathe normally, and we're going to measure how their chest expands and contracts, and we're going to measure the temperature of the air as it goes in and out of their nose. We're then going to have them hyperventilate, fast, shallow breaths, and then hypoventilate, hyperventilate, fast, deep breaths, hypoventilate, shallow, slow breaths. So on the graph, the inspirations are the peak for chest movement. So as your chest expands, as you inhale, peak. As you exhale and your chest contracts, compresses, you're going to have your valleys. For the air temperature, the temperature of the air in the room is lower than our body temperature. So as we inhale, we're breathing in cold air. So inhale, we have cold air going past the thermometer. We have the valleys. As we exhale, we're sending air that's been in our lungs, that's been warmed up by our body temperature. So we're sending warm air out through our nose past the thermometer. It goes up. So the peaks with chest movement are when you inhale. The peaks on temperature are when you exhale. So the peaks and valleys are kind of backward. They're different. They're different parts of the cycle for temperature and chest movement. So that's an important thing to know. Let's do some background respiratory physiology. So why does air move in and out of our lungs? Well, Boyles Law. Boyles Law says that pressure is equal to 1 over volume. Pressure is equal to 1 over volume. Remember, things flow from high pressure to low pressure. We talked about that a lot with our circulatory system, and now we're going to see that same principle in our respiratory system, in our lungs. When we have low pressure in our lungs, air is going to flow in. When we have high pressure in our lungs, air is going to flow out. It's all about pressure differences. If the pressure is lower in our lungs than in the atmosphere, air is going to flow towards low pressure. If pressure is higher in our lungs than in the atmosphere, air is going to flow towards low pressure and out of our lungs. So if we look at Boyles' Law, let's see, how do you think Boyles' Law pertains to this flow of air, this what we're talking about in this lab? Well, when we measure chest expansion, chest excursion, we're measuring a change in volume of our thoracic cavity, of our lungs. We can change the volume of our lungs. And by changing the volume of our lungs, we change the pressure in our lungs. If we want air to move into our lungs, we lower the pressure by increasing the volume. If we want air to flow out of our lungs, we increase the pressure by decreasing the volume. They're inversely proportional. When we inhale, we increase lung volume, which decreases lung pressure. The pressure in our lungs is lower than the pressure in the atmospheric air, so air moves into our lungs. When we exhale, we decrease the volume in our lungs, which increases our pressure to a point above the atmospheric pressure. So air moves from our lungs to the outside, just the atmosphere. All right, so Boyle's Law. We can see we increase the volume of our lungs, chest excursion goes up, that's inhalation. So changes in volume lead to changes in pressure, and the air will follow where the pressure change is. You change the volume, which changes the pressure, air flows towards that pressure. Since airflow lags behind chest movement, temperature changes lag behind chest movement. You have to have a change in volume before you have a change in pressure. So hyperventilation, we have rapid, deep breaths. Are you going to have more or less chest expansion with hyperventilation? More or less. So it's rapid, deep breaths. Deep being key. So you're taking large breaths. You're having a lot of chest expansion and contraction. So you're going to have more chest movement during this rapid, deep hyperventilation. With hypoventilation, how is the chest movement going to compare to apnea, normal breathing? Well, it's slow and it's shallow, so you're not changing your volume very much. You're not going to have much chest movement or as much expansion with hypoventilation, slow, shallow breaths. What about the temperature changes? So normally during apnea, we have cool atmospheric air moving into our lungs, and then the air warms up in our lungs, and then we exhale, and that warm air from our lungs moves out our nose past the thermistor. So we exhale warm air, we inhale cool air. Well, with rapid deep breaths, we're actually going to see a relatively smaller change in the temperature of the air we're breathing. It takes time for heat to be transferred from our body tissues into the air that's within our lungs. It takes time for that heat to pass into that air. So because of these rapid breaths, because the air is in our lungs less time, there's actually less of a temperature change during hyperventilation. I'll repeat that. Less temperature change during hyperventilation because the air is in our lungs a shorter amount of time. It takes time for the heat to move from our bodies into that air. When you cook a piece of chicken and you put that piece of chicken into a hot pan, the chicken isn't hot instantly. It takes time for that heat to be transferred into that piece of chicken and to go all the way through the chicken. With hypoventilation, we have less chest movement. We actually have more of a temperature change though, and it's because the air is in our lungs longer, so there's more time for heat to move into the air. It's like keeping the chicken in the pan a little bit longer. There's more time for that heat to move from our body into the air. So there's actually more of a temperature change with these slow, shallow breaths because the air is in our lungs longer. There's more time for heat to transfer. There's more time for it to warm up. All right, next up is the respiratory tracing calculations. So in lab, in class, we actually have one of these. So this is our spirometer. So what this does is it's going to be like what we did in the past, but we're going to be able to measure inhalation and exhalation over time with this. So you're going to see some similarities, but there's a few extra little bells and whistles added on to allow us to do inspiration and expiration and measure it over time. So we have our subject, we have our air intake tube. The air intake tube, the person will breathe into and in and out of, and the air will travel through this tube and then up underneath this bell. The bell, once again, is submerged in water in this larger chamber. So we have a large outer chamber filled with water, and then we have this bell that's like a upside down cylinder, or a cylinder that's open on the bottom and closed on the top. And air is going to move from this tube up into the bell and then back. As the person exhales, air is pushed underneath the bell rises. As the person inhales, air leaves the bell, goes back into the person, bell drops. This bell has a string on top of it connected to a pulley system. As the bell goes up, the string goes through the pulley, and the pulley is actually connected to a pen right here. This pen is drawing on this circular, it's actually a circular sheet of paper right here. And this circular sheet of paper is spinning, and this pen is actually drawing on this circular piece of paper. As the bell goes up, the pen will go down, and the line or the marking on the piece of paper will go down. As the person inhales, air is going to leave the bell, which is going to pull the string, which is going to pull this pen upwards, and we're going to see the pen draw upwards. So as the person breathes, we're going to see this down, up, down, up, down, up, the cycles of their respiratory system. If the person takes in a deeper breath, it's going to have a larger change. The pen's going to go up higher. If they have a deeper expiration, the pen's going to drop even lower. So ups are inspirations, downs are expirations, and it shows lung volumes. So right here, we have some vocab words that we need to understand for this. And I do expect you to know these vocab words. They are vocab words. We have tidal volume. Tidal volume is just our normal inhale and exhale. It's our normal inhale and exhale when we're not even thinking about it. Tidal volume. Vital capacity is what we did with the spirometers at the beginning of our experiment. So vital capacity is max inhale to max exhale. Max inhale to max exhale. We also have inspiratory capacity. So inspiratory capacity is normal exhale to full inhale. And then we have expiratory reserve, which is from normal exhale to max exhale. Normal exhale to max exhale. All right, so using this graph is very similar to the wet spirometer we used in the experimental procedures video. Just it also includes a time, well, it includes time and inhale and exhale instead of just exhale. So general notes, this recording paper on this part right here, it's actually a grid paper. So it's a grid paper, and it's going to have squares that are 1 millimeter squares. 1 millimeter squares. When calculating volumes, measure up and down vertically on the page. So volume is depicted by the vertical change in the tracing. Volume is depicted by the vertical change in the tracing. Time is depicted by the lateral change. the lateral change. So up is inspiration, down is expiration. For our examples, in what we have in graph in class, the Bell correction factor is 30 milliliters. So that's the area of the bell, 30 milliliters per millimeter. So for every millimeter that this bell rises or falls, it's 30 milliliters. So every millimeter that we see on the tracing, on the graph, every millimeter, every box up and down is going to represent 30 milliliters. The BTPS is that Bell correction factor. This accounts for changes in body temperature, atmospheric pressure, and the saturation of gas with water. So the formula is for volume is number of boxes times the Bell correction factor, so 30, times BTPS, which is 1.1. The number of boxes, how do you get that? You look at the graph and you count. You look at the graph and you count. So calculating times, so measure across the page. So time is left to right. The kymograph is the name of this piece of paper right here that we're recording this on. That is a vocab word. This should be underlined. Make a vocab flashcard for it. The kymograph speed will be given in millimeters per minute. So this is the kymograph. Millimeters per minute. So it might be 50 boxes per minute, 50 milliliters per minute. So example, 50 millimeters per minute would be 50 boxes per minute. Your measured values may be, so when we look at these examples and be ready for examples and like this on the quiz, there are a few practice problems online posted. So you should have plenty of opportunities to practice this for the quiz. But on the quiz, sometimes the drawings aren't the most accurate. Sometimes you might say, oh, well, it's halfway through the box. Do I count the box? Do I not count the box? If you are 1 or 2 boxes off, you're still going to get credit for the question. So don't worry too much about it. If you're 1, maybe 2 boxes off, you're fine. Don't be more than 2 boxes off, though. Then you won't get points. So your measured value may be slightly different than the key. However, if you have vastly different numbers, double check your work, then check with the instructor if possible. All right, so let's get into this. So here's our grid paper from the kymograph. This is what it looks like. You can see this up and down tracing with the inspiration and expiration. These lines, the kind of trend lines on top and trend lines on bottom, those are actually hand-drawn in afterwards. The kymograph, when you're recording it, just records this up and down. So you're given 50 millimeters per minute as the speed. You're given Bell correction factor of 30 milliliters per 1 millimeter. So every 1 millimeter up is equal to 30 milliliters. And then BTPS correction factor of 1.1. So what's the formula? By the way, this is just normal breathing. This is just normal breathing. This is tidal volume right here. Normal breathing, tidal volume. So we want to determine tidal volume. We want to determine respiratory rate. We want to determine minute ventilation and oxygen consumption. So let's get right into it. For tidal volume, what we want to do is it's a volume. So to calculate volume on this, it's volume or capacity is equal to number of boxes times Bell correction factor times BTPS, BTPS correction factor. So let's do it for tidal volume. We count 18 boxes up, so one cycle, how much up and down happens? 18, so tidal volume, 18 boxes times 30 milliliters per millimeter, so 30 milliliters per box, times 1.1 gives us 594 milliliters per breath. So this person, for every normal breath they have, 594 milliliters goes in and out. we then want to calculate respiratory rate. So we know that paper speed is 50 millimeters per minute. Well, let's count 50 boxes over and see how many cycles there are. 50 boxes is 1 minute. Let's count how many cycles there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 breaths, 14 cycles in 1 minute. So how many peaks are there in 1 minute? So we get a respiratory rate, 14 breaths per 50 millimeters, 50 millimeters per 1 minute. We can cross out our millimeters and we get 14 breaths per minute. Now for minute ventilation is how much air goes in and out in a minute. So tidal volume is 1 breath. So we know for every breath, it's 594. We know the respiratory rate is 14. So that tidal volume happens 14 times in a minute. So we can multiply 594 by 14 breaths per minute, which gives us 8,316 milliliters per minute as our minute ventilation. All right, so this next part, oxygen consumption. Now, to get into this, I've got to explain one other aspect of this machine right here. So the machine that we have in lab, and many models and types have this, the air before it goes into the bell will actually pass through a chamber that has special, they're like crystals that absorb CO2. They absorb CO2. So they remove any CO2 from this system. That's why this trends upwards. Because as CO2, this is a closed system. There's no air going in and out. So this is a closed system. As the carbon dioxide gets absorbed by these crystals, the bell will lose volume, like the air volume in here will go down, and the bell will start to trend downward. Because the bell trends downward, it pulls the string down, which pulls the 10 upwards. And it's that gradual pull upwards right here. Now, we have to make a number of assumptions for this. We've got to assume that the amount of carbon dioxide produced is equivalent to the amount of O2 used. So there's definitely some assumptions here. But we're going to estimate, that's a good word, we're going to estimate oxygen consumption by the amount that the graph trends upwards over a minute. So how are we going to do this? We're going to see how many boxes the graph trends upwards during a minute. So we're going to start at, our starting point. We're going to go 50 boxes over, and then we're going to go up to the trend line for where the bottom of this graph is. We're going to count how many boxes this is. So it's 17. Now we're going to go back to our volume calculator. So we have 17 millimeters. So it trends upwards 17 millimeters. We're going to multiply that by 30. So our bell correction factor. Multiply that by 1.1. And we get 561 milliliters. And that happens over a 1 minute time period. So about 561 milliliters of oxygen gets used per minute by this subject. All right, here it is written out. So here's another one that you can do for practice. The first example that we just went over was an actual student, his data when he was resting. He then went out and exercised for a couple minutes and then started using that machine in our lab again, and we got our exercise data. Practice with the exercise data and see if your answers compare to the examples. All right, so let's move on to the next part. Perfect. All right, so next up, we're going to use this graph right here in the top right of the screen. As you can see, the student, this is actual student data again, the student had normal tidal breathing and then breathed in as much as they possibly could and then exhaled as much as they possibly could and then went back to baseline. And we're going to look for inspiratory capacity. So inspiratory capacity is right here. It's normal exhale to all the way inhale. We're going to look for expiratory reserve volume. So that's normal exhale to max exhale. Functional residual capacity, which is normal exhale to no air in your lungs. We make some assumptions for this. We can't calculate all of it. We make some assumptions. Vital capacity, which is full inhale to full exhale, and total lung capacity. So let's look at this. There's 4 that we can calculate from the data. This residual volume down here and any value that requires us to know the residual volume, we can't calculate that with this machine. So we have to, if we want to know a value that includes residual volume, we have to make some assumptions. So we're going to assume residual volume is 1,000 milliliters. We're going to assume residual value is 1,000 milliliters for these examples. And we're going to calculate them. So let's start off with tidal volume. This one we've already done. This one should be fairly easy. So how do we calculate volume? Well, it's number of boxes times the Bell correction factor times the atmosphere, the pressure, temperature, the pressure temperature ratio. So we have 15 millimeters up for tidal volume. So 15 boxes up. So 15 times 30 times 1.1 gives us 495 milliliters per breath for the tidal volume for this patient. We're then going to look at inspiratory capacity. For IC, you need to measure from the end of a normal respiration to the peak of inspiration, of max inspiration. So you can see here, we start at the bottom of a normal exhale, and we go up to the peak of inspiration, 66 boxes. So we do our volume equation again. So 66 boxes times 30 milliliters per box times 1.1 gives us 2,178 milliliters per breath for inspiratory capacity. For expiratory capacity, you need to measure from the end of a normal inspiration to the peak of expiration. So from our diagram, we measure from the top of tidal volume all the way down to the bottom of expiration. So 85 boxes or so. 85 times 30 times 1.1 gives us 2,805 milliliters. For expiratory reserve volume, you need to measure from the end of a normal expiration to the peak of expiration. This is the volume of air above what you normally expire. This volume, this value, plus VC, which we have to assume is 1,000, or we do assume is 1,000 milliliters, should be roughly equal to EC. From our diagram, we measure from the bottom of tidal volume all the way down to the minimum expiration. So we start right here. We measure all the way down. So expiratory reserve volume, 68 boxes times 30 boxes times 1.1 gives us 2,244. Vital capacity. So vital capacity, you need to measure from peak inspiration to peak expiration. This is the maximum amount of air that you can move from in and out of your lungs. So 129 boxes, we do a volume equation again. 129 times 30 times 1.1 gives us 4,257 milliliters as the vital capacity. So for functional residual capacity, in order to actually measure functional, we need to make some assumptions, okay? So this is functional residual capacity. Let's go back. Functional residual capacity. So we need to figure out our expiratory reserve volume and then add that to our residual volume. So we've got 1,000 plus 2,244, which we calculated. So reserve, which we calculated in a previous example, which gives us a functional residual capacity of 3,244. Total lung capacity, we have to use that same assumption. So we do vital capacity, VC, plus the 1,000 milliliters. And so we get a total lung capacity of 5,257. All right. And I'm going to stop the video there. This last section is you are not going to be responsible for. These last few slides. And let's end on a good note. So Mr. Osborne, may I be excused? My brain is full. There's multiple practice problems up on the website. There's a worksheet also, which will help walk you through these problems. Please let me know if you have any issues with these problems. You know, I'm here to help. Come to office hours. Expect questions on the exam, on some of that material. All right, and with that, I will see you guys in the next video.